Alright, in this video, as promised, we're going to take a look at what is the same and what is different when we are working with a diverging lens. For a diverging lens, the equations are the exact same as for a converging lens. The variables are the exact same. There are a few differences in how the ray diagram is drawn. Just as in the previous video, I will here give you the three rules that we use to find where an image is formed when using a diverging lens. And then in the following slide, I will walk through an animation of how that works. So once again, we will use light rays that are coming from the top of an object. And in this case, we will then trace the ray first, leaving the top of the object traveling parallel to the optical axis of the lens. And it will refract not through the focal point on the other side. It will instead refract as though it had come from the focal point closer to the object. I promise that'll make more sense when we demonstrate it. The second ray will leave the top of the object and travel as though it is going to the far focal point on the opposite side of the lens. But it will not make it there. When it gets to the lens, it will be refracted so that it exits the lens traveling parallel to the optical axis. The third ray we will draw will be the exact same rule actually as with the converging lens, which is that it will leave the top of the object and it will pass through the center point of the lens and not refract in any way. So let's see what that looks like. We see here again the stick figure, and so we take the first ray and draw it straight into the lens parallel to the optical axis. Now, once it reaches the lens, it refracts as though it is coming from the near focal point and leaving the lens this way. So I'm going to put little X's on that ray in the part where it didn't actually travel. So you can see where the ray actually traveled is the parallel incoming and then the ray traveling up and to the right there. And the part that I just put the X's on did not actually have the light ray pass through there. Our second ray travels from the top of the object to the far focal point, but before it gets to the far focal point, it reaches the lens, which refracts the ray, so that from the lens, the ray exits parallel to the optical axis. I will now have to, again, trace backward to see where that ray seems to have come from. So the part that I'm putting X's through again is where the light ray didn't actually pass, but it appears to have passed if you are observing from the other side. Our third ray starts at the top of the object's head, passes through the exact center point. You can see me zoomed in there to see past exactly through the center point of the lens and comes out the other side unrefracted. So these three rays will diverge and never meet in the same place, and so they don't form an image. But if you trace back the blue ray after its refraction to see where it seems to have come from, trace back this red ray to see where it seems to have come from, they actually intersect right where the green ray was. And that is where the top of the image will form. Let me make sure I am being as clear as I can. This is the light ray that was traveling in from the object to the lens. When it got to the lens, it refracted up and to the right, and this ray was never actually here. This is just where the up and to the right ray appears to have come from, because rays travel in straight lines. The red ray was traveling like this, and when it got over here on the right and it hit the lens, it refracted out parallel to the optical axis, meaning that it looks like it came from back here. So the trick with the diverging lens is that you will have to trace backwards two of the rays to see where it looks like they came from. It's a little, it takes a little getting used to, but I think after walking through a couple of examples, it will make more sense. So we will make sure to do some of those examples in class. I will note that this slide looks the exact same as in the previous video, except for the image in the top right. And that's because it is. The thin lens equation and the equation for magnification are the exact same as they were for the converging lens. So again, that's really convenient. You just have to know what the variables stand for and how to plug them in. So again, let's try an example problem where you are not asked to draw the ray diagram this time. We'll do the ray diagram and some more calculations in class together. But for this, considering the ray diagram above, again, if each square is 1 meter by 1 meter, we'll calculate the image location, image height, and magnification of the image and determine the power of this lens in diopters. As I said in the previous video, you would usually be given the variables in the wording of a question, not asked to count them out off of a piece of graph paper. In this example, we happen to have to go in and determine certain things from the graph paper. The first thing I know is that the focal length of this lens is 6.5 meters because I counted out 6.5 squares from the middle of the lens to the focal point, but there's a negative there, and I've highlighted the 6.5 to emphasize it's negative. One key feature about a diverging lens is that the focal length is negative. How do I know that? Well, there's two ways that you might know that. One is that you would memorize it, and the other way is that anytime you have to trace the rays backwards to see where they seem to have come from, so that the image forms in a place that the rays didn't actually pass, that is a sign that the focal length is negative. These other two values I obtained by, again, counting the squares. So the object, the stickman in this case, is initially 18 meters from the center of the lens, and the stick figure is 2 meters high. So I'm asked to calculate the image location, the image height, the magnification, and the power. We start with the image location, and that is the thin lens equation again. So the 1 over f equals 1 over object distance plus 1 over image distance. And again, we're going to be really careful with this. The image distance will be 1 over the negative 6.5 meters. I do need the negative in there as the focal length. Minus 1 over 18 meters, the whole quantity raised to the negative 1 power. Please check my math as we did in the previous video to make sure that you're getting what I'm getting, which is that the image distance is negative 4.8 meters. The negative means this is what we call a virtual image, which just means that the rays did not really pass through the place where the image forms. If the rays really do pass through the place where the image forms, which was the case with our example with the converging lens, then that is referred to as a real image. In this case, we will see a diverging lens will always give us a virtual image, meaning that the image is negative and the light rays do not actually all come from or go to the place where the image forms. We're asked to find the image height and magnification, so let me start by finding the magnification, and I'll use that to find the image height. The magnification is negative distance to the image over distance to the object. The negative times the negative means that my magnification comes out positive, 0.27. So positive meaning that it is an upright image, but the magnification being less than 1.0 means it is a shrunken image. So I can calculate the height as the height of the object times the magnification, and I find that the height of the image is 0.53 meters, which approximately matches up with the drawing where the height of the image here is like maybe a quarter of the height of the object. That matches up perfectly. The power of the lens, like I said, is still the same equation as before, so 1 over the focal length. The focal length is negative, so it looks like I left the negative out of my work, but I have it in my answer. So the power of this lens is negative 0.167 diopters, and shame on me for leaving it out of my work. I'll fix that before I put it in the notes. You may see, if you go into the OpenStax textbook and look for their rules for how to draw these rays, they're worded slightly differently and they're presented in this table slightly differently, but they do mean the same thing. They list a total of 5 rules. 1, 3, and 4 apply to converging lenses. 2, 3, and 5 apply to diverging lenses. So you just have to, I guess, keep track of it in a slightly different way. If you choose to follow their presentation of it, you may certainly instead use my presentation of it that I've given you in the notes and in these 2 videos. They mean the same things. So, and again, we will definitely practice these. There is a point that I want to make sure we include in the notes, and that is the sign convention of lenses. For converging and diverging lenses, every distance on the object side of the lens is measured as positive until the rays reach the lens. After the rays reach the lens, every distance on the side of the object is negative, and all of the distances on the side opposite the object are positive. That's why with the converging lens example we got a positive distance because the rays actually did pass through the lens and then converge and form a distance that was on the side opposite of the object. But for the diverging lens, we found that the object distance was negative because after the rays pass through the lens, the image forms on the opposite side of where they are. As it says here, if the image is on the opposite side of the lens as the object, then image distance is positive, and the image is what we call real. And a converging lens always has a positive focal length. A diverging lens always has a negative focal length. All right, that's it for lenses, other than I think we need to practice them a little bit in class, so that's what I'm looking forward to.